In this video, we are going to prove formally an upper bound on the running time of the randomized quicksort algorithm. Namely, we are going to prove that the running time on average of the randomized quicksort algorithm is n log n asymptotically. That is, it is at most big O of n log n. And that in the worst case, the running time is big O of n squared. Well, before going into the details of the proof, let's again build our intuition. First of all, let's know that what we need to estimate is the number of comparisons. Why is that? Well, because the quicksort algorithm contains of first the call to the partition procedure and then two recursive calls. Each of these two recursive calls is going to be unwinded into the call to partition procedure and another two small recursive calls. So what is going on inside the quicksort algorithm is essentially many calls to the partition procedure. While inside the partition procedure, what we do actually is to compare all the elements of the current subarray with the pivot element. Right? So what we need to estimate is the total number of comparisons, which is not surprising because the quicksort algorithm is a comparison-based algorithm. Right? Well, now let me also explain why balanced partitions are better for us. I will explain this intuitively. So consider this toy example, this array of size 7. Assume that we selected 1 as the pivot element. So we partitioned the array as shown here on the left. Now let's see what we now know. We compared all the elements in this array to the pivot element, which is 1 in this case. So now we know that that the final position of the pivot element is just the first position in the array. So we know that 1 is the minimum value. However, we know nothing about pairs of other elements, right? So we only learned that 1 is the minimum value. Now consider another possibility. Consider the following balanced partition shown on the right. So assume that we selected 4 as the pivot element. I claim that in this case, this partition is much better for us because we saved many subsequent comparisons. So look, in this case, in the subsequent runs of the partition procedure, we are not going to compare elements 3, 1, 2 with elements 6, 5, 7. Because we already know that all the elements to the left of 4 are smaller than all the elements to the right of 4, right? And also the left part will stay in a separate recursive call and the right part will stay in a separate recursive call. So once again, balanced partitions save us a lot of comparisons that we do not need to make in the subsequent calls to partition procedure. Another thing I would like to discuss with you before going into the details of the proof is the following. Our algorithm is randomized. So its running time and its number of comparisons depends on the random bits used inside the algorithm. In particular, for any two elements, there is some probability that they are going to be compared. And using this toy example shown on the slide, I would like to just to build an intuition on how to estimate this probability, or on which factors this probability depends. So consider this small example. So this is an array of size 9 containing all the digits, and I would like to estimate the probability that elements 1 and 9 are going to be compared if we call randomized quicksort for this array. So let's see what happens. Assume that in the very first call to the partition procedure, we select the element 3, for example, as the pivot element. So what happens? In this case, 1 will go to the left of 3, and 9 will go to the right sub 3. To the right of 3, I'm sorry. So in this case, 1 and 9 will be in different parts, and they will never be compared in further calls to the partition procedure, just because they are already in different parts. Okay, put it otherwise, it means that we already know that 1 is smaller than 9, because 1 is smaller than 3, and 3 is smaller than 9. Right? We do not need to compare them. Well, and this happens if we select as our pivot element any of the elements 2, 3, 4, 5, 6, 7, or 9, or 8, I'm sorry. If on the other hand we select 1 or 9 as our first pivot element, then 1 and 9 will be compared. just because, well, if we select, for example, 9 as the pivot element, we compare it with all the elements of our array, in particular with 1. So there are 2 cases when 1 and 9 are compared. And these are exactly the cases when either 1 or 9 are selected as a first pivot. In all other 7 cases, they are not compared. This means that the probability that they are compared are 2 over 9. Okay, makes sense? Now let's try to estimate the probability that the elements 3 and 4 are compared. Well, I claim that in this case, this probability is equal to 1. And the explanation is the following. There is no element inside our array that can help the randomized quicksort algorithm to understand that 3 is smaller than 4 without comparing them. I mean, for 1 and 9, there are 7 such elements, all the other elements. I mean, if we partition with respect to any other elements, we already know that 1 is smaller than 9 because they go to other parts, to different parts with respect to this pivot. For 3 and 4, there is no such element. So algorithm just must compare these 2 elements to be sure that 3 is smaller than 4. So in this case, the probability is 1. Well, this shows that the probability of comparing 2 elements depends on how close they are in the sorted array. In particular, if they are very far apart of each other, then the probability is small. And if they are close to each other, then the probability is high. We will use this observation in the formal proof of our statement. We now start to formally prove an upper bound on the running time of the randomized quicksort algorithm. For this, we introduce the following random variable. Let I and j be different indices from 1 to n. We define xi of ij to be equal to 1 if 2 elements a prime of I and a prime of j are compared in the run of our quicksort algorithm, and to be equal to 0 otherwise. Once again, to estimate the running time of the quicksort algorithm, we would like to estimate the total number of comparisons made. So we would like to estimate for any pair of elements what is the probability that they are compared. As we discussed on the previous slide, the probability that 2 elements are compared depends on how close they are in the sorted version of our array. For this reason, we define xi of ij depending on the sorted array. We do not have this sorted array, right? We are only constructing this in the quicksort algorithm, but we use it just for the analysis. Okay? The next thing to note is the following. For any 2 elements of our initial array or sorted array, it doesn't matter. So for any 2 elements, they are either compared just once or they are not compared at all. So why is that? Why is just once? Well, if 2 elements are compared at some point, this means that at this point, one of these elements is the pivot element. Because in the partition procedure, we compare pivot with all other elements of the current subarray. So if 2 elements are compared, that one of them is the pivot. This also means that right after the call of this partition procedure, we are not going to use this pivot element. We will put the pivot element into its final place, and we are not going to touch it in any of the subsequent calls. This immediately implies the upper bound, the quadratic upper bound on the worst case running time of our algorithm. Once again, we have quadratic number of possible pairs of elements. And each pair of elements is either compared once or not compared at all. Right? So the running time in the worst case is quadratic. Now comes the most important observation of this proof. I claim that the elements a prime of I and a prime of j are compared if and only if the first pivot selected in the sub-range of the sorted array A prime from index I to index j is either a prime of I or a prime of j. Well, let's see why. First of all, when we select a pivot, a random pivot, which is not in this sub-range, then all the elements from this sub-range in the sorted element go either to the left of this pivot or to the right. So they all stay together in the same branch of of the recursion tree. Okay? So before we select a pivot which stays inside this range, all these elements stay together in the same subarray. Now assume that we selected a pivot from this subrange, and assume that it is not a prime of A or A prime of J, for example. In this case, A prime of A and A prime of J will be split apart. They will go into different parts with respect to this pivot, right? At this point, I'm assuming that all the elements in my subarray are different, and in the wall array are different. Okay? So once again, if we select, if the first selected element from this subrange is not a prime or is not a prime of A or a prime of J, then these two elements are not going to be compared, because right after the partition procedure uses this pivot from this range, A prime of A and A prime of J will go to different parts, right? If on the other hand, the first selected pivot from this subrange is either A prime of A or A prime of J, then these two elements are going to be compared, right? So this is the most important observation in this proof. Everything else is just calculation. So if this is clear, let's then estimate the probability that the corresponding two elements are compared. So we know that they are compared if and only if the first selected pivot in this subrange is one of these two elements. This helps us to estimate the probability of the fact that Xi of ij is equal to 1. Well, this is equal to 2, because we have only two choices, either A prime of A or A prime of J, divided by the total number of choices, the total number of elements in this subrange. And this is J minus I plus 1. So the probability that Xi of ij is equal to 1 equals 2 divided by G minus I plus 1. For example, if J and I differ by 1, so J is equal to Y plus 1, so these are neighboring elements in the sorted array, then this probability is equal to 2 divided by 1 plus 1. This is 2 by 2, this is 1. So and this reflects the fact that if there are two neighboring elements inside the sorted array, then the algorithm just must compare them to understand that one of them is smaller. There is no other element that can help our algorithm to realize that one of these elements is smaller than the other one. Okay? This in turn helps us to estimate the expected value of this random variable. So recall that if we have a random variable which takes only values 0 and 1, then its expected value is 1 multiplied by the probability that it takes value 1 plus 0 multiplied by the probability that it takes the value 0. Well, 0 multiplied by something is 0, so what is left is just probability that it takes value 1 multiplied by 1. So the expected value of Xi ij is equal to 2 divided by G minus I plus 1. The final step in our proof is estimating the sum of all the random variables Xi ij for all possible I and j. So once again, the expected value or the average value of the sum of the number of comparisons made is the expected value of the sum of all possible xij's, for all ij's. So the expected value of the sum is the sum of the expected values. So we can write the following, that the average running time is equal to the sum over all possible different ij of the expected values of Xi ij, and we know this expected value already, so this is the sum over all possible different ij, where j is greater than I, of 2 divided by G minus I plus 1. Well, we can take this constant 2 out and consider all possible, and consider a fixed I. For this I, what we have, j ranges from I plus 1 to n. So what we have for this specified I in this sum is a subset of the following sum, 1 over 2 plus 1 over 3 plus 1 over 4, and so on. And this is actually a known sum. This is called harmonic series, and it is known that it grows logarithmically. Once again, 1 over 2 plus 1 over 3 plus and so on 1 over n is theta of logarithm of n. Well, this means that for each fixed I, this grows, well, the corresponding sum, which ranges overall j from I plus 1 to n, grows at most logarithmically. This means, since we have n choices for I from 1 to n, that the whole sum grows asymptotically as n log n. Okay, and this concludes our proof.